making great sound from thin air, and will involve a discussion of how modulated ultrasound can be used to create basically an air driver, which is what we'll be hearing about. Our speaker is Dr. Moti Margalit, the CEO of SonicEdge, so please join me in welcoming him.
Thank you very much for coming to listen to the talk. And I'll tell you about the technology that we have invented to make a new type of speaker. If you look at the world of speakers, really not much has changed in physics since they were invented. The same principle, a membrane moves, pushes air, generates pressure, and that's how we hear sound. And not much has changed since Alexander Graham Bell or others, and we read, invented that nearly 150 years ago. Materials, components, technology, much has changed in the engineering, but the physics remain the same. And the problem is that when you try to make a small speaker, you run into physical limitations. You try to balance the resonances, you try to make a lot of air move, it doesn't work. And the result is when you go to a smaller speaker, you typically would pay a penalty in the performance of the speaker. So when we started thinking about this problem, we went back to first principles and asked ourselves, what can we do with a really small speaker? So naturally, a very large speaker like a subwoofer is good for making low frequency sound. If we go to a tweeter, we can get higher frequency sound. And if we go to the ultimate, and this is this type of speakers we have in our system, this is the width of a hair, and 50 microns, and this is actually very good for making ultrasound. So we work around 400 kilohertz, and this is generating ultrasound into the air. We can modulate the source of sound, we can put songs on top of this, but we can't really hear it because everything is in ultrasound and beyond our ability to hear things. So what we do is, this is a picture of our device, and you're looking at an array of these structures. And what we do in these structures is modulated ultrasound. So let's understand how that works. If we look at the basic ultrasound driver, it is emitting a signal much above what we can hear. We can hear in the green, and this is emitting something in the ultrasound regime. How can we take that ultrasound and make it into sound? So in the past, people have done what's called a parametric speaker. They used so much ultrasound, the air becomes nonlinear, and you have self-modulation. We took that concept of modulation and said we can do it much more efficiently. Instead of modulating using nonlinearity of air, which is inefficient, requires a lot of power and so forth, we can do active modulation. So we have a structure where the ultrasound goes through this aperture, and then we can open and close an acoustic channel with a second membrane. And by this way, we can attenuate the ultrasound or let it go. I'll show you that in a slide. But the result is that we're transferring energy from the ultrasound into the audio regime. So by doing modulated ultrasound, we're transferring energy from the ultrasound to audio, and now we can hear the music that we put on the ultrasound. So this is the basis of our technology, active modulation of ultrasound. And this is the first time people have suggested doing this. Before, there were the parametric speakers, but they were using nonlinear modulation, which is not efficient and has many challenges. We're using active modulation, which is very efficient and actually results in a very good speaker. Now, you can rightly say, okay, that's a nice story, but why does this make a smaller speaker? And the answer is that the same structure, we can look at it from a slightly different perspective. And this is actually an air pump working at 400 kilohertz. So it's pushing air very quickly. This enables us to build up sound pressure. If you compare this to a standard speaker working at 1 kilohertz, we have 400 times the advantage. What you see here is an attempt to depict the fact that we are building up the sound pressure by pulses coming out at 400,000 times a second. And by doing that, we're replacing the size of the speaker with speed. So instead of moving slowly, but with a large membrane, we can move very quickly with a small membrane. Now actually, just to make an analogy, this was the breakthrough in Dyson vacuums. The reason Dyson could make much more efficient, smaller vacuums which run on batteries was because they were using very high-speed pumps. So again, we are just taking other stuff from places, but implementing it in the audio regime and coming up with a very novel speaker. So the air driver, because it doesn't really have a membrane, these membranes are good for 400 kilohertz. At the audio regime, we're just pushing air. This is one of the advantages. We don't have any vibrations. No motor is moving at audio frequencies. Everything is happening in the ultrasound. So a standard membrane pushes air at audio frequencies. We push air at 400 kilohertz. If you compare, we have 400 times the advantage at 1,000 hertz, but then we have 4,000 times the advantage at 100 hertz. And this is a unique feature of a pump speaker and an air driver, that as you go down in frequency, you actually have increasing sound pressure level, and I'll show you a graph of that. But this speaker is a full range speaker. It can go from a few hertz all the way to tens of kilohertz. This is not like other MEMS speakers, which are typically good for the high frequencies, so they complement the dynamic driver. Our speaker is a full range solution, does not require a dynamic driver. One speaker handles lows and highs. And since this is done in silicon, it can do to sound what LEDs have done to lighting or transistors to electronics. Today we're at the flashlight level. Right? We're making solutions for IDNs and AR glasses and small solutions, small audio solutions. But this is a very scalable solution. So the same way that you today light everything with LEDs, in the future you can use our speakers in larger and larger formats just by scaling it up. So again, this is a picture of our speaker, and the technology, the underlying technology that we make it is called MEMS, micro electromechanical systems. This is the same semiconductor industry that we use the chips to drive our computers or to drive our audio equipment, but now implementing a mechanical structure. And what's unique about our approach is that we actually use the same manufacturing infrastructure as the MEMS microphone. I don't know if you're aware of the MEMS microphone, but about in 2005, this field started, and today more than 8 billion MEMS microphones are manufactured. They are actually the dominant microphone you'd find in your phones, in your earphones, in your laptops, or even in your cars. So we are using the same infrastructure. Our manufacturing partner is making MEMS microphone. Our packaging partner is packaging MEMS microphones. And we have the scalability of this to go to tens and even hundreds of millions of units per year. So coming back to the modulation operation, we have the ultrasound speaker. So the ultrasound speaker is emitting the ultrasound that's going through this acoustic aperture. And this is a situation where the modulator is open, so ultrasound is free to flow. If we lower the top membrane, the modulator is closed, and the ultrasound is attenuated. So this is the modulation function. By using this modulation function, we have the transfer of energy from ultrasound to audio. As I mentioned, we're using silicon technology, so the same semiconductor material that's used in electronic devices. And it's pure silicon, not because, of course, the silicon needs to be pure, but some of our competitors are using PCT. So they are driving the silicon platform with piezoelectric material, a material which deforms when you apply voltage to it. we're using electrostatic. So we are using pure silicon, just silicon. And this is actually pretty important because if you want to be ROS compliant, which means you do not have any lead in your components, you need to go to pure silicon because PZT, actually one of the components of PZT is lead. And that is a problem for some consumer companies. We're using exactly the same process as the MEMS microphone. And this gives us an advantage because this is a well-established industry, making billions of microphones a year, and we're just riding on top of it and enabling the next level of audio components to come out of the same production lines. And sustainable, this talks about I would say, the global drive also to reduce the use of magnets, rare earths, which is not sustainable. So an electrostatic drive implies that we ground the middle membrane. All the membranes are conducting. We ground the middle membrane and apply voltage to the top and bottom membranes. We apply two sources, one at one frequency and the second at the second frequency. And what we hear out of the device will be the frequency difference. So for example, if this is 400 kilohertz, this is 401 kilohertz, this will emit a 1 kilohertz signal. And you can see the functionality where the top membrane is constricting the acoustic channel, and as a result, picking out the right pressure at the right time to generate sound from ultrasound. So, unfortunately, if you try to drive a MEMS chip with today's DACs, it won't work. Today's DAC put out an audio signal, and we need an ultrasonic signal to work. So we provide an electronic chip to convert the audio signal into the ultrasound and modulation drives. So the algorithm to drive the chip is embedded in the electronic chip, and the audio input coming in here can be analog or digital, is converted into ultrasound and modulation signals right in the MEMS chip. In the floor show, we have this as an evaluation board. By the end of the year, this should be a chip. The algorithm itself is surprisingly not very complicated. Essentially, you take the audio signal, you multiply it by ultrasound carrier, and that goes to the ultrasound speaker. The modulator or demodulator simply takes the carrier, and the function that our chip does is multiply one by the other. So if you have the signal multiplied by a carrier, multiplied by a demodulation signal, you get back the original signal. And that's the output that we get out of the system.
So the signal, sorry for the question, the signal being applied to the modulator, which is the one that's facing the listener, right? This is static, right? It's only playing the carrier frequency.
It's not static, it's playing the carrier frequency. So
Right, but the frequency does not change.
the frequency does not change.
It's independent of the input signal.
Exactly. This just demodulates the signal.
Yeah.
At least that's the simple way to go about it. Yeah.
It's very simple.
Okay. So this, of course, adds, you can say, some complexity. But let's think about the advantages of this. If you think of a speaker, it's actually a very broadband device. It's working from a couple of hertz all the way to 20 kilohertz. So from, let's say, bandwidth perspective, this is an extremely broadband signal. We're working at 400 kilohertz. Take that same 20 kilohertz and put it at 400 kilohertz. It's a very narrow band signal. It's less than 5% less than the carrier. So all the complexity you have in the audio regime goes away when you're doing processing at the ultrasonic regime. It's a narrow band signal, and there we leverage some other tricks, like the fact that we're using the resonance frequency of these membranes. Again, the resonance implies something that's narrowband, but 20, 30 kilohertz at 400 is narrowband. So we get more movement with less power because we use the resonance effect, but we don't pay any penalty like you would have if you use a resonance speaker like a BA. You're good for one frequency, but not much beyond that. So the ultrasound, even though it sounds a bit complicated, it actually simplifies a lot of the processing and a lot of the way that we handle the signal. And what we get is superb linearity. I'll demonstrate that in a second. And we take away the complexity because we can provide this algorithm or this chip to companies who work. So this is the type of response we get in the ear coupler. And this device is coming from the fab, so actually all of them look exactly the same. You don't need to mix and match anymore. They're all the same, and the response is the same, both in frequency and as well as in SPL. And what you can see here is something that you won't see from any other speaker. This is the pump effect. As you go.
It's not a source of pressure, it's a source of acoustic flow.
Constant flow, exactly. It's constant flow from 0 all the way to tens of kilohertz. So actually we can go down to very low frequencies, and this will simply go up. Okay? Why is this going? It's going up at 20 dB per decade as a constant flow. The lower the frequency, the more time we have to build up pressure. Okay, this is the same 400, 4,000, and so forth. So we can provide very good performance at low frequencies. These are the resonances of the coupler, and this then goes up to 20, 30, 40 kilohertz. I have not plotted the phase here, but it's also very simple to plot. It's basically a flat line, because this is just a constant volume velocity source. There are no resonances anywhere in the audio regime. And again, I don't have the plot on that, but the intrinsic response and the group delay is less than 1 microsecond. Everything is happening in the ultrasonic regime. We're just moving air in the audio regime. That's why we call it an air driver. And just for comparison, I put here a 6mm driver with a 3 kilohertz resonance. But you can see it's trying to mimic the volume velocity source, but it can't really hit it. And then this is a 13mm driver optimized for ANC, so it has good performance at low frequencies, but then because of the larger diameter, it drops off. After resonance, it has a harder time to provide the SPL. This is just to demonstrate the linearity, so you can see that the SPL curve does not change, it just drops in a very linear fashion across all the frequencies. And this, of course, makes it much better to reproduce sound across all frequencies. You don't need to be concerned about how to optimize the electronics and do it dynamically. And as asked here, so how do you do an acoustic design using this approach? Well, typically the speakers we use are a pressure source. So we would have a voltage over here, and then we would have all the resonance, all the passive components like the tubes or air cavities. They would be designed using lumped element over here. Our device is a current source or a volume velocity source, so it's a current source, and it's just providing constant volume velocity into the earphone device. So same acoustic principles that we use to design acoustic systems today are used here, just replace the voltage source with a current source. So that, just to summarize the advantages of this technology, it provides the highest SPL per area compared to any other technology. It has no vibrations in the audio frequencies. It has a very linear response, extremely wide bandwidth. You can go below 5 hertz all the way to more than 40 kilohertz. The responsivity and the group delay are very quick. The intrinsic performance of the device is really very, very sharp. Everything is happening at ultrasonic frequencies. And finally, it's a solid-state speaker. So it's made in silicon, very scalable. We make one, we make many, they're all the same. And if you look again at the world of the MEMS microphones, the fact that we're all the same makes building arrays of these very easy because they are consistent. And if you want to do beamforming, you don't need to care about the resonant frequency of the array. They all have exactly the same phase response, very easy to tune and have good arrays. So that's the summary and the opportunity for any questions. Yes?
Okay, I have a very possibly stupid question, but I'm not great at fluid dynamics. At those kind of scales, being that small and when you package it, is there a possibility for like cavitation where you like starve it of the air that it needs to move?
So that's an excellent question, but if you do the calculations, we're actually working in very low pressure, low speed regimes. The air moves at a couple of meters per second. The maximum, let's say, pressure we get in the cavity between the two devices is less than 1,000 Pascal. So even though everything is very small, it's actually not going into the extremes. It's true this technology can scale, and we've demonstrated this to work in many other platforms, including piezo, and we've taken this up to speeds of 40 megahertz, and it still works. So you can actually make a speaker that's 10 times smaller or 100 times smaller. There are other advantages and disadvantages to do that, but in principle this is a very scalable technology. And as you go to the, let's say, at 1 gigahertz, you will run into those issues. But in our regime, there are no such issues.
I have a lot of questions. Feel free to stop me when you would need to share something that you would not want to share with your competitors. So I work for USAN, by the way. You know USAN. This is purely analog input, right? So that you're not using the digital sound generation where you activate individual membranes like what the Pixel is doing, yeah.
So no, this is purely analog. All the membranes work together.
You feed it a purely analog signal and you move it in an analog way, right?
Yes.
Yeah. I noticed it didn't show any absolute SPL values.
Those we do share under NDA.
I got it, okay. Follow-up question again. You don't need to answer. This being a source of velocity, presumably, you mentioned 400 kilohertz being the carrier, presumably that's somewhere where the resonance frequency would be. How leakage tolerant is that? As in, if the volume of air between the diaphragm or the membrane and the eardrum is not sealed anymore, how much does that drop off?
So in a similar way to a standard speaker, the impedance of the cavity has an effect, but as a volume velocity source, you're, I would say, agnostic to the impedance. That means you give the same volume velocity for different configurations. In that respect, we are much more leak tolerant than comparable speakers up to the 10 millimeter level.
Because the actual movement of the speaker, or the movement of the speaker is relatively independent of change of the load.
Yeah.
Okay.
So we can accommodate leakage, and actually an interesting thing to note is that the speaker itself is inherently leaky, because there is always a connection between front and back.
Right.
Even though we are basically leaky, you saw the glass. We have the nice, so up to a certain level we can accommodate can accommodate leakage. Of course, open air as a volume velocity source, this is essentially a 20 dB. Yeah. And maybe, I don't know if this was maybe not so well understood, but typically when you design an IEM or earphone, you have the situation where the cavity is occluded, so that means it's well sealed. And in that situation, most speakers can reproduce the bass response. The problem is that that's not so comfortable for long-term use. And to make it more comfortable and, let's say, more natural, some leakage, some interaction between the ear and the outside world is introduced. And in that situation, the speakers need to work much harder to generate the required sound pressure level, because when they push the sound pressure into the ear, some of that is leaking out. So in the smaller speakers, let's say the 6mm speakers, would typically work in an occluded situation if they want to have good low frequency sound. But the larger speakers, the 11mm, 7mm, can also work in leakage situations, and they can still reproduce the low frequencies. Our speaker, because of its unique behavior, it's a volume velocity source. So it's not creating pressure directly, it's creating flow, and from that flow you get pressure. And this changes somewhat the characteristics, makes us a bit more tolerant to leakages, and makes us a bit more, opens up opportunities when we're looking at this for free field speakers. So when you do a free field speaker, the physics of a cavity are turned around, and you get a slightly different behavior, but then this is a source of moving air, and we can manipulate this source to get also good response from free field speakers.
Actual implementation to a product that will be in our ears?
That's
a question of time.
Yeah, okay.
so. We have on the floor, we have some I would say engineering samples,
Okay.
and we've been working with customers now for under NDA period, so I can't disclose exactly.
So when you say customer, it's who we think of as manufacturers?
Yeah, you would call them manufacturer or a brand name, and we expect to see products in the field in the market next year.
Awesome.
As a follow-up to that, how many of those drivers are in this?
In this one, 150,
Okay.
and then what we show on the floor were 400.
Okay.
But it's really scalable. I mean, following up the question previously, there are, in the past, people have talked about what's called the digital sound reconstruction. So they looked at the structure like this and said, okay, we have so many pixels. If I want low pressure, I'll operate one. If I want high pressure, I'll operate all of them. Now, that makes for a very complex, because now you need to address all the pixels, so that adds a lot of complexity. And then when you scale it up, it's not so easy to scale up because you need to think how you will implement the movement across the pixels. All our pixels do exactly the same thing. And if we have 4 times the size, we'll have 4 times the SPL. So 12 dB more.
Is there any significance behind the hexagonal shape of them?
No, it just packs nicely in space.
Right.
You notice these on speakers have the exact same hexagonal shape?
Yeah.
So the limitation of silicon is that you need a rectangular shape. I mean, square or rectangular, because typically, well, you cut it in, but that adds to complexity and cost. Well, there's the actuator and the beam around it. You have the actuator and the beam around it. a hexagon cut is what, 6 cuts instead of 4.
It's tricky, but it's doable.
But
Yeah, it's easy.
having said that, there is the flexibility of size. So you can have it rectangular, you can have it in any shape you want, and it will have the same performance. The only thing that's important is how many of these we have. And keep in mind that the audio wavelength is much larger than this. So there are no, for good and bad, but there are no array effects from this. They're just working together, and from an audio perspective, this is a point source or a dipole array because it's pushing it on one side and pulling it from the other side. Yes.
I know you were talking about products a little bit more, and I don't know if you noticed, but I know on the show floor, Creative has a MEMS driver in the in-ear headphones. Is this the same technology, or?
So it's so you have the other MEMS speaker company in front. The MEMS speakers that you have in the market today are the same principle of standard speaker. That means a moving membrane, pushing air, and the actuation mechanism, the stuff pushing the membrane is based on MEMS technology. So that is the speakers that exist today. What we do is different because we use the modulated ultrasound principle. So our sound generation mechanism is totally different, and then we implement it using a similar platform, the MEMS, microelectromechanical system. So we use the same manufacturing platform, but the sound generation technology is totally different. Yes.
On your slides, you described a lot of the advantages of this technology over the common speakers. Are there any disadvantages you know that you'd be willing to share with us? Any disadvantages?
Disadvantages. Well, that's a good question. There are some disadvantages, but I would say the biggest disadvantage is the fact that everything we do is new. So from the algorithm we derive to convincing customers to adopt it, it's an uphill battle. I would say we found customers very receptive, but still, we can't use off-the-shelf drivers, we can't use off-the-shelf even acoustics. Everything is tuned to this technology, and at the end of the day, that of course I would say increases the hesitation to adopt. But we're working on that, and hopefully, like I said, next year you'll see the products in the field.
All right, thank you.
Can you talk about scaling up in size? How hard is that? So IM versus headphone versus speaker versus PA.
Okay, so up until, I would say, all the hearable world, we can address using this technology.
The what world?
The hearable, everything that sits on your head, we can scale and be cost competitive even with the larger drivers. I would say probably even micro speakers for cell phones. The receiver for sure, the speaker maybe, because as speakers move more and more, we need to compensate for it either by getting more SPL per area or increasing the area. You can see here that, and this is actually a real-life implementation, as you can see on the screen. A lot of this area is open, so the fill factor, the area we actually use is not so great. So already here we have a potential to increase the sound pressure levels from a given device. And then there are other design aspects we can use to further increase the SPL. So we can address the micro speaker world using this technology in the coming years. Going to larger speakers, like if we want to have a full cabinet of them, I think it's not a question of, it's more a question of economics than a question of capability. we can scale up and we can make larger speakers. But then it's a question of, if you're replacing a $10 speaker with an array of a couple of hundred speakers, can you meet the same cost targets? And that, I would say, is an open question. To address that, we are also looking, but this is more into the future. You could make this technology instead of on silicon, which is good for smaller stuff, you can make it on glass. And then the same way you make TVs, you can make this kind of speakers. And this has no vibration, so you can put it on the wall, and you don't have to worry like the electrostatic speakers or other speakers that do vibrate. So scaling up, that would be the way to go. We're not there yet, but we're optimistic. Any other questions?
Thank you.